let's talk a little bit about symmetry. Okay, so just the basic idea here is, well, we know what symmetry means, right? I mean, our mastery of the English language tells us that symmetry is when things are the same on both sides, right? So if we were thinking about x-axis symmetry, we would want something to be the same on both sides of the x-axis. So if I had a point right here, and if my coordinates were x, y, if I wanted to know what point is symmetric to this one about the x-axis, we're just going to flip it over that x-axis. So the coordinates for that point, well, they're going to have the same x-coordinate, but it's going to be y units away from the x-axis. So it's just a reflection about this, about that line. So the coordinates here would be x comma negative y. So we would have the same x value because they're the same vertically, or I guess the horizontal location is the same, but the vertical location is just different, right? So we're essentially taking our paper and folding it over this x-axis, and hey, this is going to lay right on top of that other one, right? So this is x-axis symmetry. If we talk about y-axis symmetry, we can do pretty much the same thing. If we've got our coordinate plane, I've got some point right here, call it xy. If I wanted a point symmetric to this one about the y-axis, I would just reflect it over the y-axis. So we're going to have the same y value, but our x value is going to now be negative. So we got negative x comma y. So the point symmetric to this one about the y-axis is here. So we just made the x coordinate negative, right? And that's how we found it. Now, we've probably seen x-axis symmetry and y-axis symmetry, maybe in a different context before, but we might not have seen what origin symmetry is. Origin symmetry is where it is reflected, well, about the origin. So it's going to be, we kind of think of origin symmetry in different contexts and different classes. Sometimes we think about it as a rotation. Sometimes we think about it as a reflection, then another reflection, or a reflection, then another reflection. But essentially, we're just going to take this point, and we're going to do both of the things that we just did here. So we're going to make the we're going to make the y value negative, and we're going to make the x value negative. So any point at all, x, y, its reflection about the origin, we would just take the negative x and negative y values. So maybe we can do an example with an actual point. So if I wanted to take this point right here, let's say -4, -2, and I wanted to draw its reflection or the point that is symmetric to it about the origin, I would make both of these values negative. So a negative -4 would be a positive 4, and a negative -2 would be a positive 2. So now these 2 points are symmetric with each other about the origin. All right, so just individual points, this isn't such a crazy idea. But we want to test an equation for symmetry. So I'm going to put this up here. This is on page 26 of your textbook. To test the equation for symmetry about these various things, we're just pretty much doing what the pictures imply us to do, right? So if we're going to test for symmetry about the y-axis, I'm going to slide this up here. We're going to substitute negative x, y into the equation and simplify. If the result is equivalent to the original equation, the graph is symmetric about the y-axis. So what this means is if the result is the same, or we can show that the result is the same as the original equation. I mean, it's not exactly the word the same, but we can think about equivalent as meaning same. Anyway, we can see that here, right? if we substituted, and what that means is the point is going to be on the graph, right? So if I put in a negative xy in there, is that one on the graph as well? And we can go down the line here. The x-axis one, we're just going to substitute x comma negative y, and that's implied by our picture. And so is the one about the origin. So if we plug in negative x, negative y, we ought to get something equivalent as well. So let's look at an actual example here. How about x minus 1 square plus y square equals, I don't know, 4. So we want to test for symmetry. We may recognize this shape as a circle. We may not. Depends on our background and what we've done thus far. But we should be able to do this independent of whether or not we know what the picture looks like. So if I want to test for y-axis symmetry, I'm going to put negative x in for x, and I'm going to leave y where it is. So I'll put negative x instead of x. And then we can look at it and say, well, is this equivalent to what we started with? I mean, it might be. Maybe we can simplify what's going on in here. We might be able to do that. So I don't know, maybe we can take a negative out of here. And then we can simplify this, right? The square of a negative is positive, and then the square of this is just going to be the square. So we got x plus 1 square plus y square equal 4. And then we have to go and say, is this equivalent? Or is this the same as what we started with? And of course, this is a negative sign, this is a positive sign. So we say, no, it's not equivalent. So there is no y-axis symmetry. Period. Okay. So there's no y-axis symmetry here. So we just substituted a negative x in for x, and we checked if it was the same. All right, x-axis symmetry. And we're going to do the same thing here, or a similar thing. We're going to take the original equation, and instead of a y, we're going to put in a negative y. So the thing you need to be careful about, well, you always need to be careful about this, is grouping symbols, right? Because the square is going to the whole variable here. It's y, and we're plugging in negative y for y, so the square is affecting the whole thing. So grouping symbols are important. Okay, so we can simplify this a little bit. That's just going to make it positive. So we got x minus 1 square plus y square equals 4. And then we check, is it equivalent? So we reference back to our original equation, and it is. It's the same. So we say, yes, it is equivalent. So then we say there is x-axis symmetry. So if we were going to go and draw a picture of this, we would know that it should look the same on both sides of the x-axis. Okay, and we can check for origin real quick too. We can probably see what's going to happen just based on what we observed with the y-axis portion of this. If we put in a negative x and a negative y, we're going to see what happens. A little bit off the page here. Okay, so from our work on the left here, we know that this simplifies to just x plus 1 square. We know that that simplifies to y square. So now we have to look if this is equivalent. And we pretty quickly say no, right? Because we'd have a minus sign in the original equation. This one has a positive sign, so it's not equivalent. So no origin symmetry. All right, so really all it boils down to is plugging in the appropriate negative and checking for equivalence.